Right. In the previous module, we started talking about solution dynamics, and then we went on to talk about solution dynamics of water. That is where we stopped, and we did not go into a lot of detail, but we said that if you take bulk water, then the ultrafast solution dynamics that you see there is not single exponential, it is tri-exponential or bi-exponential with a Gaussian component. And in Fleming's work, they have actually been able to assign each of these components to different kinds of motion of water, including rotational motion, librational motion, and so on and so forth. And your homework was to read that 1994 Nature paper and understand it. We also said that in confined medium, the solvation by water becomes slower by orders of magnitude, and that is explained. Once again, we did not go into much detail, but it is explained mainly by Bakchi's model, one of which is exchange between bound and free water. So, today we will discuss a different aspect of water. What we will do is we will show you the vibrational spectrum of water, and then we will discuss the different normal modes of water, not isolated water, but water as water liquid. And there we will try to see what happens when one of the vibrational modes is excited. How does the energy get dissipated? How does it get redistributed in different normal modes of vibration and libration? And this work is mainly by Elsisser's group, and our present discussion will focus on these three papers that are listed here. There has been more work, so it is up to you to go and read more recent literature in this topic. So, to start with, let me show you a vibrational spectrum of liquid water. And here the only difference between this and the vibration spectra that you usually record is that y axis is absorbance, not percentage transmittance as it usually is with IR spectrum, but this is a regular steady state FTIR spectrum. Now, here you see three major features 1, 2, 3, and you see a broad feature here and a broad feature here. So, what are they? This one I think everybody knows, the one between 3000 and 3600 700 centimeter inverse, that is the OH stretch of water. That is the strongest signal, and that is what predominates whenever there is anything that contains an OH group. You always see this broad absorption, that is very, very well known. The next one also I think is well known, it is OH bend. The third broad absorption here, along with this even broader and less prominent feature, is ascribed to libration. As we had perhaps talked about in the last module, librations are restricted rotation. So, you have water molecules that want to rotate, but then since they are hydrogen bonded, they are brought back. So, it is sort of wagging motion, and we are all familiar with wagging motion in a molecule for IR. So, here this is not within one molecule, but it is in the intermolecular coupled system. A particular water molecule wants to rotate, but is brought back because it is hydrogen bonded. This kind of motion is called librational motion. Of course, energy of this librational motion would be much lesser than your stretch or bend, and here it is. This is actually called the L2 band, the prominent librational motion, low frequency librational motion. Here you have some high frequency librational motion, which is not very well defined, but will play an important role in our discussions. And what are these A, B and C? We will come back to that later in a couple of slides. So, the question that we are trying to trying to understand is this ultrafast dynamics involved in coupling of these modes. Generally, what is the meaning of normal modes? That these modes of vibrations are independent of each other, but in a correlated system, associated system, when you make one vibration happen, it does affect the other vibration. So, you can think that what happens when hydrogen bonding is stronger, what vibrations will be affected. What happens when this bending takes place? It affects the hydrogen bond dynamics, right. The moment it affects the hydrogen bond dynamics, that is going to affect librational motions as well. Librational motion will be more or less depending on what happens to the hydrogen bond. So, this is basically what we want to study, and the reason why you have coupling between normal modes is, if you look at the energy diagram, this is what it is. This one is OH stretch, the biggest energy gap. This is OH bend, and this is librational motion. They might remind you of some asymmetric vibration, but the energy gaps are really, really small. As you can see, this is the energy gap between 0 and 1 for OH stretch. This is the energy gap between V equal to 0 and V equal to 1 for librational motion, much smaller. And the notable feature here is, if you look at the energy of V equal to 1 of the OH stretch manifold, that has more or less the same energy as V equal to 2 of OH band, right. So, what happens when they are close? What is it called? What are the symmetries of vibration of water? Now, C2 is the point group. So, what is the symmetry of this OH stretch? Symmetric stretch, asymmetric stretch, all that thing is there, right. So, symmetric stretch is A1. What is bend? You better look up. So, what happens here is that since there is an energy match and there is a match of symmetry as well, you have something called Fermi resonance. In Fermi resonance, energy can, there is coupling between the modes and energy can get transferred between one mode and the other. So, it is not unusual to expect that if you excite OH stretch, energy will go into OH bend as well. And then librations have so many energy levels, it may be quite expected that no matter which one you excite, there will be energy transfer to librations as well. So, finally, when you make water molecule vibrate, say excite the stretch, that will that energy, you give some energy for it to stretch, right. That energy will be dissipated by exciting bending motion and librations as well. And the times involved are always ultra fast, because this V equal to 1 lives for about 200 femtosecond. This V equal to 1 for OH band lives for about 170 femtosecond, and we will see what happens when we look at the normal modes, how they evolve. Okay. So, just a reminder, L2 libration is rotational motion hindered by hydrogen bond. So, if this L2 band shifts to lower frequencies, what does it indicate? That means hydrogen bonds are weakened. Yeah. So, these are things that we will be looking for. OH bending mode. Now, OH bending mode, generally we do not even pay attention to this in bulk water, because each water molecule in any case is surrounded by so many water molecules. But when you are going to make measurements in femtosecond time scale, you need to take into account a little more of a detail. And if you are going to work with water clusters where you have a small number of water molecules which you can prepare artificially, then also this becomes important. This is what is actually known from this water cluster kind of experiment. It is known that OH bending modes first of all depend, the frequency of the OH bending modes, it depends on number of intermolecular hydrogen bonds per molecule. So, if it is equal to 4, then you have a higher frequency vibration. If the number of intermolecular hydrogen bonds per molecule is less than 4, then you get a shift. So, therefore, seems to be a sort of a magic number here. It does not matter whether you have, well, how many can you have per molecule, that is another question. There is a reason why 4 is a magic number. How many hydrogen bonds can be there for water? There can be 4, right, you cannot have more than that. So, if it is not 4 for some reason, then if some hydrogen bonds are broken, then there is one kind of lower frequency vibration, and if it is 4, if whatever number of hydrogen bonds could be formed is formed, then you have a higher frequency vibration. So, this is something that is known. So, the important pathway for energy transfer to surrounding hydrogen bonded network would be of course by coupling with intermolecular librational modes. So, the experiment that is done is pump a particular vibrational mode and probe all vibrational modes. So, this is an IR pump, IR probe experiment. Okay. Pump by a femtosecond pulse in IR, not visible or UV, and probe in IR as well. With that background, we can come back to the earlier diagram, and now I can tell you what these are. This A, B, C, these are the these are the spectra of 3 kinds of excitation frequencies used. When you excite by C, and I will tell you what the wavelength is, then you essentially excite OH stretch. When you excite this by using B, you excite OH bend. When you excite by A, you essentially excite libration. Of course, it might have been better if you could excite here, but there might have been a limitation of the experimental setup. Okay. And these are the frequencies then 3150 centimeter, and remember what I showed you earlier is a spectrum, not a here this is actually a spectrum, same scale, and you will remember that a femtosecond pulse cannot be completely monochromatic, there is always a spread of energies. So, what we are showing here is the modal frequency maximum of that spectrum, IR spectrum. So, when you excite the OH stretching mode, that has been done by using pulses which have maximum at 3150 centimeter inverse. OH bending mode is excited using 1650 centimeter inverse maxima pulses, and high frequency librations are excited by 1350 centimeter inverse. Okay. Another reason for not exciting low frequency libration is that, I mean, where will the energy go? You can only have librations if you pump at low frequency libration, right. Only when you excite something at higher energy can that energy go to lower energy modes. If you pump a lower energy mode, that energy cannot, you cannot have joining up of photons in this case at least. Okay. So, remember this is a spectrum, and this is a truncated spectrum actually, as I think the probe had a little bit of limitation, and in any case it makes no sense to probe the OH stretching mode. The only thing that you can see there is a ground state bleach that is going to recover. So, here the study is focused on mainly 1650 centimeter inverse, what is that? OH bending mode, right, and here you have all the librations. So, what do you have before going into each of these quantitatively? If you see when you excite the OH stretching mode, remember OH stretching mode is how much? 3150 centimeter inverse. You get a bleach at 1700 centimeter inverse or so. What does that mean? Why would there be a bleach when you pump the, why would there be a bleach for the OH bending mode when you pump at OH stretch? You are pumping OH stretch and we see there is a ground state bleach in OH bend. Why would that happen? And this is not nanoparticle, nothing, we will talk about nanoparticles later, this is just liquid water. What is the meaning of ground state bleach? In this case, population at V equal to 0 goes down, population at some higher vibrational level goes up, that is a hint. Total population more or less the same. Stretch, yeah, we pump by stretch, then what happens? I have actually shown you the result already. You have to connect with what I have shown you, something that I have shown you. Depopulation of bend, why? Remember Fermi resonance? What happens in Fermi resonance? So, there is direct energy transfer, that means population of V equal to 2. Yes, population of V equal to 2 of OH bend takes place by direct energy transfer from the stretch. Remember? Yeah. So, I pump here, right, and that is V equal to 1. So, there is energy transfer, right. So, some population of V equal to 2 will be there. So, naturally there is depopulation of this OH bend, energy transfer is taking place. So, it is an excited, well, vibrational excited state phenomenon that would cause that ground state bleach. And here you see this transient absorption, positive signal also coming for OH, that is because of population of higher state. Okay. So, there is this Fermi resonance, this is a clear signature of that. Now, what happens here? There is ground state bleach of L2 as well, and there is ground state bleach here, little bit of growth here, difficult to analyze this data, but it happens. So, that means, since there is a bleach of L2 vibration, that means L2 vibrations are also, they also get excited, that means energy gets transferred from stretch to bend and also to libration. So, the question is it direct or is it two step? Now, what happens when you excite OH bending mode directly? So, here also you get a ground state bleach which is expected, because you are exciting that particular vibration, and you get this excited state absorption, that is also expected. Once again you get a ground state bleach here, And here you see it is a little different, you see a build up, the build up is stronger in high frequency liberational mode, you see that a little better, which means when you make the molecule bend, what is happening? Hydrogen bond network is affected, and that is what will affect liberation as well. That is what is taking place. That is also sort of energy transfer. And what happens when you excite high frequency liberations? Once again there is a ground state bleach here, and once again there is this lower frequency transient absorption. Remember what we said about this higher frequency and lower frequency business for bending motion? Yeah? Yes, if number of hydrogen bonds is less than 4, then you get this lower frequency absorption. So, that is why, so this might seem a little strange that I am exciting lower energy liberations and I see a ground state bleach in comparatively higher energy bend. That is because by doing this, exciting this lower energy liberations, high frequency liberation, what you do always is that you they are moving like this, right. So, hydrogen bonds will get affected, they will be weakened. That is why you get this phenomenon here. So, this is something very interesting, because you might not at first glance expect it, right. You might think that you excite lower energy, what will happen? This is what happens because we are not working with isolated molecules here. It is a hydrogen bonded associated liquid. And again you see there we see a rise of high frequency liberation, again we see a ground state bleach here. Now, qualitatively I think we understand what is going on. Quantitatively, if you look at the traces, this is what you see. When you excite high frequency liberations directly, the rise is actually instantaneous. This little bit of what looks like a slope, that is because of the instrument response function. You are not using a delta pulse anyway. When you excite OH bending mode, do you see the rise? Yeah, this one is instantaneous. Now, compare this with this. This is the instantaneous part, and there is a rise. Why is there a rise? Look at this energy diagram once again. You excite the OH bending mode, it lives for 170 femtosecond, and in this 170 femtosecond, it can either come back to V equal to 0 or it can transfer energy to liberation. The rise time that we get here is about 170 femtosecond, which means that almost all the energy that you provide in OH bending goes into liberational mode. That is why that higher V states of liberation actually grow. It is no longer just instantaneous, a little bit of instantaneous part will always be there, because remember we are working with non-monochromatic pulses. So, direct excitation is bound to be there, and then you are exciting this high frequency liberations as well a little bit, but that rise is very prominent, and the rise is 170 femtosecond. When you excite OH stretching mode, then you see that instantaneous part decreases even more, and just to the eye, hasn't the growth become more prominent and hasn't the growth become longer? Yeah, you can see it if you compare these here. So, here what happens is, in fact, there are two rise times. Now, analysis of this kind of data is always problematic. To fit a rise time itself is a non-trivial task. In order to fit kinetics to more than one rise time requires a lot of confidence. Because as you know, if you increase the number of parameters, it is going to fit better anyway. So, your data quality has to be very good, and you must be very confident about what you are doing. You must make sure that you are just not making up some story that is not right. So, there again model becomes important, and two rise times here sort of okay, because here you see two kinds of energy transfer. One is from here to stretch to bend, and then from bend to here. Okay. So, again we are only providing you an overall view of this paper. Please read the paper and see how the data is analyzed. So, what they have done really is that they have fitted the entire thing to a kinetic scheme. So, it is like an intermediate, right, A to I to P. When you do that, you get a kinetic equation, and that is what you have to fit your data to. You cannot just fit to two rise or anything. Okay, that is what they have done, and they have extracted the two times. They turn out to be 170 and 200 femtosecond. So, this is the thing when you pump high frequency librations. Okay, I do not have to go through each part of it, but when you pump high frequency libration, this is what happens. You get a broadband enhanced absorption rising towards small frequency, which means again energy transfer is taking place. And here you get this less than 100 femtosecond decay, that is limited by the laser pulse, and a very weak 0.9 picosecond component. So, that slow component is there, it is not as if it is not there. 0.9 picosecond means what? 900 femtosecond. Okay, so you might not seem very slow, but it is at least slower than less than 100 femtosecond. So, what this means, this broadband enhanced absorption, not easy to handle. What it means is that when you excite the high frequency librations, then part of the energy goes right away and part of it goes a little slower, which may not be unexpected, because there is always a period of this kind of librational motion. 600 to 950 centimeter inverse, there is a fast bleach, and that is because of because there is a shift of libration L2 band to lower frequencies. See what is happening here? Here something is rising, is not it? Do you see that the signal becomes more than 0 at the very end beyond 600 centimeter inverse? So, why is there a bleach here? There is a bleach because due to high frequency librations, one thing that definitely happens is this hydrogen bond network is disrupted. So, like bending, libration also moves to lower frequencies if hydrogen bond is disrupted. That is why you see that bleach. And OH bending absorption, there is a slight shift to lower frequency, that we have already discussed why. When you excite OH bend, then in early time you get a bleach of V equal to 0 to V equal to 1 transition, time constant is 170 femtosecond, broad absorption at lower frequencies. Later, for longer times, you see there is a rate shift of this absorption and liberational absorption gets reshaped. Why does that take place? Once again, because of disruption of hydrogen bonded network, okay? And that is what is sort of discussed in this last paragraph. And finally, when you excite OH bend, you see an instantaneous rise in the 1400 to 1610 centimeter inverse, 1400 to 1610, and initial decay is 170 femtosecond as discussed already. This is a V equal to 1 to 2 transition of the OH bending mode, 1 to 2. Longer times the signal is due to overall rate shift of the liberational absorption. Okay. And OH stretch, I think we have already discussed this Fermi resonance, we do not have to go through it once again. So, finally, the story that we get is that of coupled vibration, and this is I like this because it is a good example of how one can use a pump probe technique to look at very intricate interactions that take place in a coupled system. So, there they have looked at water because water is ubiquitous, that is the liquid of life, but one can think of experiments that one can design similar experiments on things that are more complicated. Of course, IR experiment in presence of water, if you want to look at motion of biomolecules for example, this could be a good way to go. The complicating factor there is that biomolecules are always in water, water always has its very strong absorption because it is a solute anyway, it is present in much more. So, unless you have absorption in some other region, it may be difficult to follow, but it may not be impossible. So, finally, this is the picture that has come out of the whole study. You excite this, I think this is taken from a movie that must be available in the somewhere on the website or in the associated contents of the paper, but you excite in 100 femtoseconds. This is the situation. Hydrogen bond, if I put it very qualitatively, what happens is that within the first 100 femtoseconds, the hydrogen bonding network is weakened, and then longer times 3 picosecond or so, hydrogen bonds actually get broken, and that is what shows up in this rate shift of bending vibration frequency and in shift of liberational frequency as we have discussed. So, that is the story of how energy migrates from one mode to the other in associated systems like liquid water. So, I do not know whether anybody has followed this up later on. It might be interesting to look at, well, forget biomolecules for the moment, even water. So, water confined in a reverse micelle, or water at the surface of a protein, bound water. What kind of energy migration do you have in case of bound water or inside a vesicle, or maybe inside a cell for that matter. But of course, for that if you want to do it inside a cell, you have to work with an IR microscope, not impossible, but it is just that we do not have it. IR microscope coupled with femtosecond IR pulse, that is a problem. But this paper is important because the thing is, unfortunately, in today's world a lot of research is driven by impact factor, which is completely wrong, and this paper is published in JFSChem A, which is the least impact factor journal in the JFSChem family, but it does not matter. It is very good fundamental work, and I think it is an indicator of a lot of possibility that can open up in this kind of experiments for, especially for water in confined environments and perhaps for other molecules as well. Okay. So, that is what I think is one of the most important pieces of work in this field in the last 10-15 years or so.